Okay, welcome back, everyone. Are we ready? Okay, let's go. Engineer Abdelrahman and Engineer Omar will proceed with the next session, which is going to be hands-on. So get ready to start working yourself.
Please drop your questions in the chat and they are gonna answer them, but try to make your questions proportional to the notebook, but not outside the scope of the notebooks, so everyone can benefit from those. So we avoid now asking advanced questions about physics or anything. Just to try to ask a question within the hands-on, and we keep and save those questions for later sessions.
Engineer Abdelrahman and Engineer Omar, are you with us?
I think Engineer Abdelrahman is now stepping in, and I think Engineer Omar is in the session, or perhaps maybe he's still in. Yeah. Okay, Abdelrahman is here, and
Yeah, Omar should be with us, but maybe away from the laptop.
please drop your questions in the chat, and then Engineer Abdelrahman is going to answer them, and potentially when Engineer Omar joins as well. We got the first question. What is the role of the variable backend name?
Okay,
Abdelrahman, you are muted. So we have the first question about what is the role or what is the meaning of the backend name variable in the notebook.
Okay. Hello everyone. I'm Abdelrahman ElSayed Ahmed, quantum software engineer and quantum machine learning researcher, education need at AGC community, and an instructor. Okay. First, I need to thank Cairo University and Dr. Ahmed Shawi for this invitation and the collaboration. Okay. For the first question, for backend here, backend name within the execute circuit function, there are 4 modes. The backend name one only is being used when we are dealing with a real QPU from IBM. We choose which hardware we want to run on it. There are several options. IBM, I can show the options from IBM here. IBM Quantum, quantum computers. There are several backends. Can show I need to sign in first. Okay. For the free plan, there are three hardwares: IBM Fizz and IBM Breeze.
Abdelrahman, I think you are muted.
Can you hear me?
Yes.
Yeah.
Eng Ahmed Salim has shared a list of the backends for IBM. Yeah. So for your IBM plan, you choose which backend you want to run on. If you are on the Pro plan, there are more powerful backends, more than that. Yeah. So this is the rule for the backend name. Okay, I will show the code for how to run on real backend. In the function, execute circuit. Where is it?
Abdurrahman, you want muted again. So I don't know if something happened automatically or.
Yeah, it's weird. So I was saying in execute circuit function, when you choose your mode, QBU, and any backend, it automatically initiate the Qiskit runtime service, then the backend, then transpile your circuit into the architecture or topology of the backend, and then run the circuit using sampler and gets the results as counts. It's like a dictionary, state, and how many times it was measured. Uh, so all you have to do, take this function and mode QBU backend name. Let's say IBM Brisbane. And you have to create an account on IBM Quantum Computing Platform. I believe I had an account. So when you create an account, you can then create an API token, so you can initiate the Qiskit runtime service. Okay, for the measurement, let's see. Share screen. Okay, for the part for the measurements. Okay, this part. You you're talking about the 0 and 1. 0 and 1, these are the indices for the qubits. So it means measure qubit 0, which is the first qubit, and also measure qubit 1. So it's like a list for the qubit indices, and this is the classical bits indices. So measure qubit 0, and the result put it in classical bit 0. So it's measure takes two arguments. First, a list for the qubit indices, and second, the classical bit indices. So
Rahman, you are muted again.
Yeah, yeah, Abdelrahman, you are muted.
I have shared the group for our community on WhatsApp, and you can follow our LinkedIn pages for iCafé and the community on LinkedIn.
No, please, for the school, not all the people in this school are on the group on the WhatsApp. So please share in the chat.
Yeah, okay. I have shared the WhatsApp group on the chat, and I will now share also the LinkedIn.
And of course, for the takeoff communication, we can also create a little WhatsApp group if this will be handy for everyone for the school.
So this is the link for iCafé, and the link for our community on LinkedIn. Okay, Mina, you have raised your hand. Go ahead.
Yeah. Hi everyone. Thanks for taking the chance to put such brilliant content and people of expertise to be in to meet and offer the chance so that all of us can benefit and like uh, um, like take the expertise and the knowledge from such brilliant minds. Throughout my life, I have learned that if I have a big problem, let us break that into smaller ones. So, could someone from the leaders of the meeting to walk us through the notebook and break the sections into little things or little parts and explain what happens behind the scenes? That would be uh, a great uh, um, effort or like a great thinking.
Okay. Okay. Now I'm sharing my screen again. I will go through the notebook slowly with explanation for each cell. So if you are running on Google Colab, so you will run this first connect to connect the Python environment. I will go step by step. Okay, now it's connected. So we'll run first this script. If you're running on Colab, you need to add exclamation mark. So it will install all the Qiskit libraries that we need. Okay, running away. Could you please tell me which line is the code that enable me to know the first value of qubit, if it's 0 or 1 before running the circuit, or it's always 0? Okay, we will go through this question when we are explaining the notebook. So after the installation is done, we can run the second cell, the imports, everything correct. Two of the most famous libraries, NumPy and Matplotlib, and for our framework Qiskit, we will import this quantum circuit that will create the circuit itself that has a quantum register and classical register. And from Qiskit circuit random, there is that function that is random circuit that create a random circuit to show. And from Qiskit quantum info, we'll import state vector, enables us to see
Yeah,
the state
Abdelrahman, sorry
vector.
for the interruption. Can you enlarge
Yeah,
the font a bit? Can you zoom in?
yeah, no problem. Yeah, okay,
Yeah, great. Yeah, thanks.
great. Yeah. So the state vectors after each gate or operation. Without measurement, we can see the state vector itself. So it's like analyzing the circuit after each operation. And for visualization, there is a plot histogram, takes the counts and plots the state with the counts for each state after the measurement. This is for Qiskit. Second library, Qiskit Air, which allows us to import air simulator and noise model. For air simulator, it's the main engine that simulates the circuit on our classical computers. So we can then, after we ensure it's correct, we can run on the real hardware. It takes many arguments. It can take state vector, so it's run exactly the state vector without shots. Shots means that we run the circuit itself and we initiate a number of shots, let's say 1000 shots, then we run the circuit for 1000 times and we get the counts for each state from the measurements. So it's called ideal simulator. What if we want to add some noise or simulate some noise? We import noise model from Qiskit Air Noise. So it allows us to add some noise from fake backends that Qiskit also provide, so we can see and observe what noise can do to our simulations. Okay, this is for Qiskit Air. For Qiskit IBM runtime, one of the most two important methods, quantum runtime service and sampler version 2, allows us to run the circuit on a real quantum processing unit or a real hardware from IBM. And if we want to test our circuit on a simulation, but with, let's say, a noise model from a previous hardware, also Qiskit IBM runtime provide us with some of fake backends with noise models, so we can test on them on classical our computers before actually running on real hardware. On our case, we are using fake Manila version 2. It's a 5-qubit fake backend. And lastly, Qiskit transpiler generate a present pass manager allows us to transpile the circuit so we can compile it and run it on real hardware. So this is all the information that we need for our imports. Okay. Our version we are using the latest version. It's 2 weeks out, 2.4. And our first function, execute circuit, takes the quantum circuit that we have constructed and our mode. We will see what mode here means, and a number of shots if we are running shot-based simulator or a real hardware, and backend name. So if our mode is a state vector, first we need, if we let's say created our circuit with 1 qubit and hard-marked gate and then measurement. If we are running on using a state vector, there is no running the circuit, so it's just let's say matrix multiplications all the way. So there is no measurement. So first we will remove the measurements from our circuit, and then here in place equal false, it means so it create another copy from the circuit, so don't override the current circuit, create another copy without the measurements. So if let's say if it's 1 qubit hard-marked measurement, so it will strip out the measurement and it will be 1 qubit and then hard-marked. Then return the state vector from instruction. State vector from instruction takes the circuit, then does the matrix multiplication all the way to the end, and then return the state vector itself. We will see an example of, after we are done. Or let's see, for our case, let's say I have run this circuit now. Okay. Let's say I will create a circuit Q1 equal quantum circuit with only 1 qubit and 1 classical bit, and then apply Hadmard. Then apply Hadmard on the first qubit, and then we apply measurement. I don't want that. So there is measurement on the first qubit, and it will measure the bit itself, or the output will be on the first classical bit. Then we can actually see the circuit output ML. So this is the circuit, a very simple circuit, 1 qubit, 1 classical bit, applying Hadmard, then measure. So let's say we will execute using state vector. Print, we will see the output. Print execute circuit Q1. This is a circuit. Our mode is state vector. Let's just take it, copy from there. And that's it, I believe. So we don't here shots. Let's just add a default value so it won't. So this is our output. We execute the circuit using state vector mode. So the output is a vector to y1 vector with there was actually a better way to show the circuit draw, I believe. I don't actually remember the. Okay, so this is the output. It's a state vector. So the first initial condition is 0, 1, which is state 0, and we apply Hadmard. So let's just erase that. Okay. So when we apply Hadmard, which is 1 over square root 2, 1, 1, 1, negative 1, on 1, 0, the output will be 1 over square root 2 and 1, 1. So this is actually our output here. So this is the real value. Let's just, okay. This is 1 over square root 2, and this is 1 over square root 2. So the output only applies matrix multiplication without actually running the circuit. So this is what state vector do. Okay. Our second mode, which is ideal, which we initialize our simulator, which is air simulator. This is our simulator. Then initiate and generate a present which transpose the circuits, so it can run on the back end. Our back end here is the simulator itself, air simulator, and optimization level. There are several optimization levels. If you want to run the circuit as it is, you just make it 0, or you can not. You can just delete it. I don't know, make a copy here. So, but in our case, there are 4 optimization levels: 0, 1, 2, 3. Each optimization level makes the circuit more feasible on our on hardware, but it takes more time for the compilation, and the efficiency couldn't be as the state vector and the ideal case. So we transpile the circuit using optimization level 1, and we call it BM, and our circuit, or T circuit, which is the transpile circuit, we run the circuit, run it using the circuit as an argument, and we return the simulation, our simulating run the circuit itself, the transpile circuit. So we transpiled it, and then we will run the circuit. I just want to show, I want to take this out so we can see each step, what is actually happening. So we initialize, here we initialize our simulator, then we initialize our, let's call it our tool that will transpile the circuit, any circuit, and we'll create, we'll transpile our circuit, which is Q1. So what actually happens to the circuit after the transpilation? Let's take a look. Draw output equal MPL. So in our case, because it's only a one gate and optimization level is only one, so it's okay, nothing happens. So we can increase the optimization level up to 3. Let's see if there is any difference. Okay, the circuit is very simple, so it doesn't have any optimization to be done. So after we transpile the circuit, we will run the circuit using our simulation. So the steps, we create the circuit, then add measurement. So we can, after running the circuit, we will get output, initiate our simulator, initiate our tool that we will be used to transpile our circuit, transpile the circuit so it can be run on backends. Then this is optional to draw. Then lastly, we will run our circuit using the simulator and number of shots. Let's say I will run the circuit for 1024 times. After that, I will get the results, and from the result I will get counts. So this is out. Counts, get counts will be a dictionary or a hash map or a map or anything like that. So it tells me I have measured 1 how many times, 526 times, and 0 498 times. So this is for the our ideal case. So this is actually what happens on the back end if we want to use our ideal. So let's say we want to add some noise for our simulation. Here we initialized air simulator, but here we initialize first our fake backend. Then we will extract the noise from our backend. Let's say it's FAC vanilla version 2. We'll extract the noise model using noise model from backend and enter the backend. So we now have the noise model itself. So then we will initialize our air simulator with the noise model. And all the steps are the same for our ideal case. Okay. So if we want to run on real hardware, first we need to initialize Qiskit runtime service. Here I will just I put it at the end. Yeah, here. So to save your account, you have to run this command or this function one time in your environment. So I will run it with you right now. I have this my account on IBM Quantum Platform. This is actually my educational account. So you have an open instance, 10 minutes for using quantum hardware per month. So you will take CRN copy and input it at here instance. And for API, I will create an API token here. Let's call it Cairo, yeah, for example, and then create copy, paste it here. So now this is now I run this cell and then remove it. So I don't have to run it again because my account now is saved on this instance. Of course, if you're running on Google Colab, everything will be erased. I'm talking about if you're running on your local local PC or local laptop. So now our account is saved. Where is the function? So execute circuits. Okay, it's here. So after saving as account, you can then make an instance of Qiskit runtime service as a service. Then it can list all the backends that I can access. So let's run this here, for example. Backend service.backends. So I can access IBM Fizz, IBM Kingston, IBM Marrakesh. As I can see, these are actually the 3 backends that I can actually access on my open instance free plan. So I will choose, for example, IBM Fizz, ticket copy, and then when calling the function, I call it here. Okay, where is it? Yeah, this is a circuit, the same circuit we will call execute circuit, but now I will choose QBU and 1024 shots, and then the backend will be IBM Fizz. Yeah, okay. Execute circuit is not defined. Let's run this. I don't need to show this again. So it will initialize the service, then takes the backend. So now I have choose IBM Fizz, so it will this backend will be IBM Fizz. So then call the generate present bus manager to transpile the circuit into the backend that I have chosen, and then this is a transpiled. Then when we are running, we're not running on the air simulator is just for simulation on your computer. If you are running using a real hardware, you will use sampler version 2, and then your mode will be the backend that you have created. Then after that, from this sampler will run the circuit. The circuit here, you can batch many circuits as a batch. Here it's like a list. Let's say you have 10 circuits, you can run them all at the same time with the same shots. Here the list only has one circuit, and then after running, it will save the result from the job, and then result we will this command, the result is a big dictionary. So the first index have data, has values, and you can get the counts from that. So let's actually test that. Execute. I have, no, it's not like that. Okay, so now let's see if it's actually running on real hardware or not. So okay, as we can see here, this is the job I have submitted. This is a cloud provider, so I have run, let's say this is my name, this is a job, this is the hardware I have used, sampler. It takes 5 minutes for the total completion, but only 2 seconds on the quantum hardware itself. And this is the output. Output 0, 525 times, and for 1, 499. So now this is the job has been completed, and the results have come. So I can save the results, and actually each job has an ID, so you don't have, if the results has, let's say it has been erased or something, you can get the job and you can from this job get or fetch the results back. So this is how to run the circuit. We have run it on using state vector and ideal simulator and noisy simulator on a real hardware. So let's this is a helper function. It runs the circuit and also displays the output. So only what it does, it takes the circuit and makes a copy of it, and it's the same mode and shots and backend name, so nothing different. Executes the circuits. Then if it's a state vector, just output the state vector itself, and other than that it will be a dictionary. And plot histogram actually takes the results and you know output it like a plot. So we can actually try it right now. Let's try it for what actually happened here. Let's see what actually plot histogram shows. Execute circuit. We will not use quantum hardware again. We will use ideal for our case. So plot histogram, when running the ideal simulator, it shows like a dictionary, but let's say we have so many qubits, so many states, we can't observe our counts correctly. So plot histogram will show us it's like a plot, so it's easier to observe the results. Okay, so this is all what Injo Omar has been explaining: superposition, entanglement, circuits, more examples, 2 qubits and 2 classical bits, single qubit gates, how to actually apply single qubit gate, Hadamard, NOT gates, Z gates, showing the circuit, rotation gates. Okay, what else? So this is ideal, and then yeah, applying 2 qubit gates. 2 qubit gates, for example, this is C0 takes the first qubit, which will be the control qubit, and second qubit will be the target qubit. So it's like that. First qubit, which is actually index 0, index 1, the same for any 2 qubit gates. And then for the measurement, measurement, you can actually call, let's see here, to measurement. No, I don't want that. There are measurement all, measure all, I believe. So when you call measure all, it measures all the qubits into all the classical bits. But let's say you don't want actually to measure all the qubits, you want to measure a subset of qubits. So you can add them in a list as an argument. So you tell the function measure qubit 0, qubit 1 into classical bit 0, classical bit 1, and then draw the circuit. Yeah. And here random display using ideal. This is the example for half adder circuit. Yeah. We can actually run on, let's just for fun run it on a real hardware. QBU shots, and let's use IBM Fizz again. Okay. Shots. Where is the function? Back end name. Okay. So let's see. There is an error. Oh, we haven't actually run the cell for run and display. Run and display is here. Yeah. Okay. Let's run it again. Let's see our job has been submitted or not. Okay, our job here has been submitted in progress. Estimated time 2 seconds. It should be done right. Okay, it's completed right now. So as we can see here, on our ideal case, it was all the shots 1-0. So there are no noise. There is no noise. So when we are running on a real hardware, we will see there are a bit of noise, some states that shouldn't be there, but overall, let's say it's 94% correct 1-0. So the same here. It's also other gates showing the results. So are there any questions about the notebook after this explanation?
Actually, we have a couple of questions, but we are running late again. But let's pick up some important questions Dr. Ada Dahi and Dr. Naha Mutawa are asking about. Dr. Gada is asking about the maximum number of qubits available for this platform. And when you answer, please answer for both the simulation and the real hardware. And also Dr. Maha Mitawa asking about her IBM account. She has an IBM ID, and she is asking if she can use it for this platform or not.
Yeah. Actually, to make an account on IBM Quantum platform, you have to have a IBM ID. So it will work, but for the, let's say, for the open plan, it has an expiration date. Mine, it will expire in 300 days. So I don't know how old is your account, but when you are signing in for IBM Quantum platform, you try your IBM ID. If it doesn't work, you can create a new account. So it's an easy task. Okay.
And about the available number of qubits in both the simulation case and the real hardware case.
Okay. For simulation, it depends on your actually local hardware, CPU and RAM, but I can say it runs very well until 20 plus qubits. After let's say 25 qubits, it will crash the laptop. It won't give good results if your circuit has a big depth. For the hardware, for open plan, all three hardwares are 156 qubits. Okay.
Thank you. I think we need to take another break, and we will again make it a short break, not the 30 minutes. Just take 15 minutes, and then get back for the third hands-on session. Dr. Taha, agree?
Yes, we take a break and then we convene with quantum machine learning. So we continue. So was a question in the chat what we do with this. So what we learn now, we get familiar with the syntax of Qiskit as a software development kit, and what engineer Abdelrahman and also engineer Omar have outlined is that how to use this and how to run and execute on a real hardware. And then with this knowledge, you are gonna use it to make a use case. So like what you are gonna see with Abdelrahman shortly, how to run and program in quantum neural network to make a fit or interpolation.
Okay, so we take 15 minutes and we convene back at 9:15. Yeah, 9:15. All right, thank you all.
Yeah.